Hello there. Today we're looking at DeepSeekMath, pushing the limits of mathematical reasoning in open language models. Now this paper is a bit older. It's from, as you can see over here, from the 27th of April, 2024. Nevertheless, it introduces something called GRPO, the Group Relative Policy Optimization, which is also a component in DeepSeek's R1 model. And since everyone is in DeepSeek craze right now anyway, I thought we'd look at this paper. We also discuss this paper in the Saturday paper discussions every Saturday, almost every Saturday on our Discord. Join us. It's fun. And it's always a good discussion. And yeah, if you want to present some paper, we're more than welcome to address the group. All right. I've left some notes in from that paper discussion, as you can see, but don't let yourself be distracted. We'll handle it. As you can see, the paper is ultimately aiming to win at math. So this is the top one accuracy in a math benchmark. So this is a benchmark where you get some kind of high school math problem and you're supposed to figure out the answer to that problem. Like John has 4 apples and hands off 2. Now, how many does he have? Or more complicated questions in, things like algebra, geometry, and so on. But there's always some kind of task and then some kind of answer, and that answer can be accurate or not accurate. Like it can be correct or not correct. So you have a good method of scoring these models. Like it's like scoring whether they get the correct answer. And as you can see, the model they end up with, which is their DeepSeekMath 7B, so 7 billion parameters, is on par with some of the most, largest and most advanced, at least at the time, publicly available commercial APIs like GPT-4 and Gemini-Ultra. And for all we know, these are massive models that have been, trained on various proprietary data set, and yet the 7 billion parameter models outperforms them. Now, to be said, the big models are general models, meaning they can do whatever, and this math model is specifically tuned for these kinds of math problems. But still, it is quite an improvement over all other models that have been specifically trained to do this task, and it is quite an improvement over the generalist models that are typically, not so bad at this stuff. So how did they do that? They do this by I would say a 2-prong approach. First, they collect a very high quality data set for what they want to do, and they collect a lot of that data. So they have a method that allows them to scale data collection while keeping the relevance and quality of the data high to the task that they want to do. And on the other hand, they introduced this GRPO, which is a variant of Proximal Policy Optimization that has a few benefits over Proximal Policy Optimization. Notably, you don't need a value model for GRPO, which means that an entire model to train falls away, and you get to use all that memory and compute on your main model. All right, let's dive into it. So the first thing they do here is they collect a data set. They say here they create a data set called DeepSeekMath corpus, a large-scale, high-quality pre-training corpus comprising of 120 billion math tokens. They extract this from Common Crawl. Common Crawl is a giant data set that is simply crawled websites. So website crawler collecting all kinds of websites, dumping them, and or dumping the links. I'm not entirely sure what the data set exactly contains and what you have to go download, but in any case, it's just a random huge pile of website data, and out of that they draw this data set. Now, what's interesting about this is that they don't go about, creating synthetic data. They don't go about creating new data or something like this. What they essentially show is that there is a lot, and this 120 billion tokens here is going to be many times larger than any comparable data sets. So like an order of magnitude larger data sets than other targeted math data sets. So what they show is essentially there is enough good data even in like internet dumps. If you can just get it out, if you can just move through that data in some particular way to find the high quality data, you can achieve very, very good things. So to anyone who's working on fine-tuning such models for, particular domains or particular tasks, this is a very important result because, yeah, it shows that the data is technically there, and by selecting it well, you can get a very large performance boost. They do this in an iterative fashion. So we'll jump right into the section where they do that. Here, data collection. As I said, the process of constructing the DeepSeekMath corpus, it's an iterative pipeline that demonstrates how to systematically gather large-scale mathematical corpus from Common Crawl. So they start with what they call a seed corpus. A seed corpus is a small set of relevant data to your task. Now, there's two problems with the seed corpus. First of all, it is small. As usual, like, for example, this open web math data is a collection of high-quality mathematical web texts, but it's small. Someone has collected it, so that's one problem. And the other problem, it's usually not diverse enough. So rarely is there a small data set that exactly aligns with the domain you want to fine-tune on. Either it is related to it or it's a subset of it, but the diversity is very often not there in most kind of constructed data sets. So most data sets that are not collected but constructed are geared towards a very, very specific subset. Like think even something like ImageNet, which at the time was huge, right? It was only a tiny subset of object classification because it focused mainly on dogs. It focused on a very particular type of picture, namely a picture where there was largely one object and it was kind of in the middle, and it focused on very particular kinds of labels and classes. So while ImageNet is a great data set, it's only a small subset of what you would kind of call visual recognition, the broad task of visual recognition, even if you talk about object recognition. So the goal is to take this seed corpus and expand it both in size and in quality. How they do that? They do that, as I said, in this iterative method. So starting with the seed corpus over here, they first train a model. They train a fast text model, which is like a text classifier model, very scalable, very kind of lightweight, but usually powerful enough to do these kinds of tasks. So they take the seed corpus and they take random other web pages from Common Crawl and they train a discriminator to discriminate between things that are like the seed corpus and things that are unlike the seed corpus. Specifically, I believe they take about 500,000 data points from the seed corpus as positive training examples and 500,000 web pages from Common Crawl as negative training examples. Then they train a classifier to split those two. One criticism, or well, not criticism, one comment here is that sometimes in these kinds of things, something called hard negative mining is employed. I did not read any of this here, so it must have been good enough. But it's sometimes, let's say you just train a classifier between this seed data set and random websites. What can be is that the random websites are so different that a lot more stuff gets classified as positive than you would necessarily like. And then you have to resort to hard negative mining. So maybe, here is math, and then here is like, I don't know, gardening, which you also sometimes have to calculate, how much dirt you need, how much fertilizer, and so on. And, here are all kinds of other random websites. If you train a classifier, it will like split through here if you equate them. And so you have all this gardening content on your positive side. So yeah, there are other ways of constructing this so that you get a more narrow boundary here. But if it's not necessary, then good. So using this model, they now sift through Common Crawl. They have a kind of a cleaned, deduplicated version of Common Crawl that they do, which consists of, I think, like 40 billion websites. So through that, they sift and they classify with their model. They explicitly say they only retain not just stuff that the classifier labels as positive, but they say we rank the collected pages according to their scores predicted by the fast text model and only preserve the top ranking ones. So by modulating that threshold, you get to control kind of how close to the seed corpus you are. And they say we choose to keep the top 40 billion tokens in the first iteration. So that's a first iteration. Sift through all of the corpus using your classifier, keeping the 40 billion tokens that rank the highest, and that's it. So now how do we get from 40 billion to 120 billion? So now they have an extended corpus. And then they say, okay, we discover what they call math-related domains. So they use the fact that we are collecting websites here. And websites have a URL, and that URL is usually something like, google.com/blah, blah, 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 reddit.com/blah, blah, 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 pets.com/blah, blah, 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 blah. Okay, so what they do is they say, we assume that largely, given a domain name, the following pages are somehow related. And therefore, like in pets.com, it's very clear they all revolve around, some certain amount of topic. So when we now group all of these 40 billion, or of this 40 billion entire Common Crawl set, we group into their domains. So we do a big group by their domains. And then we see, so if within one domain, let's say you have something like mathexchange.com, right? If within one domain, we count the number of websites that have been classified as positive, like that have remained in our data set. And if more than 10% of domains under a given domain name, of URLs under a given domain name have been classified as positive, then we reconsider the entire domain. Okay, so it's essentially an expansion step. You assume that if more than a certain threshold of URLs inside of a domain have been classified as a particular topic, it's very likely the entire domain at least has some relation to that topic, and you should consider the other URLs in that domain as well. You should kind of reconsider, even though your classifier didn't classify them. So that goes into here, an annotation process. Now, I was not entirely sure how that annotation process goes exactly. So they say we manually annotate the URLs associated with mathematical content within these identified domains. I'm not sure if that means like humans actually sift through it and annotate them. I don't know if they do it based on the URL itself or actually going to look at the websites, or if they have some LLM as a judge or something like this. But there is some sort of external entity looking at all of these things inside of all of these URLs again, and deciding whether they should be part of the corpus. So this is where you expand your diversity, if you will. So you reconsider stuff that hasn't been considered by your classifier, and you expand within these domains. And that then goes into your data set, and that becomes the seed data set for your next iteration. So again, you train a model, and now what happens is that because here you reconsidered a whole bunch of stuff and added that to the data set, now your model has a broader scope. Your model has a better idea of what you want in the data set just beyond that initial seed corpus, and therefore is going to classify more stuff as positive. You can choose to keep more tokens than just the initial 40 billion ones, and go again. And if you do this clustering by domain again, you will all of a sudden notice that, yeah, for example, let's say github.com, in the first iteration, it was maybe just 2% of websites that were classified positively by the classifier, and therefore it's like, nah. But now that you added kind of all of Math Exchange because you reconsidered it last iteration, your classifier's kind of idea of what consists in what the data set is broadens, and therefore it might be that in this round, like all of a sudden 12% of GitHub falls into that category. So that means that in this next step, you are going to reevaluate all of GitHub. And again, through that annotation process, add additional things into your seed corpus for the next round. So you can see how this slowly, iteratively broadens the scope in size, because the classifier is able to kind of annotate a lot of web pages given the seed corpus, and in diversity, because once a domain is annotated enough, you reconsider it and you add a bunch more stuff that wasn't classified by your classifier. So it kind of pushes itself up. Now, there are two possibilities here. Possibility one is that this goes on forever and ultimately you'll have the whole internet in your data set, right? Because you just keep expanding, keep expanding, keep expanding. Possibility two is that, in fact, through, this manual annotation process here, having some idea what they want, that this is going to converge to some stage where, okay, everything that the model tags as positive kind of is already within the domains that are considered, and no new domains are being added from the last iteration, and therefore the manual annotators, they see nothing new, which means the model gets no new data and so on. So it kind of stabilizes. And in this particular case here, it seems that exactly the second thing is true, which is lucky, because otherwise, where do you stop? But they say, after 4 iterations of data collection, we end up with 35.5 million mathematical web pages, totaling 120 billion tokens. In the 4th iteration, we noticed that nearly 98% of the data has already been collected in the 3rd iteration, so we decide to cease the data collection. Okay, so now we have a data set. Now, what do we do with the data set? Well, we train a model on it and see how well it goes. So not regarding any sort of reinforcement learning or any sort of instruction tuning, the first step that they do is just kind of a validation experiment, just taking a base LLM, in this case, a smaller LLM, 1.3 billion parameters, and training it on, for one, their data set that they collected, and on the other hand, on a bunch of other data sets right here that are available for these kinds of questions, and they see what happens evaluating on several benchmarks. So this is the resulting table right here. Now, what you'll see is that the data set trained on and the benchmarks are different, and I think that's important right here, right? If you train on the exact data set of the benchmark, then sure, you're gonna do well, but that's not what we're after. We're after some kind of generalization, and therefore this is, you train on something else, then you evaluate. Now, in this table, you can see if you do no math training at all with this base LLM, you get some scores, relatively low scores. on various things. Now, if you actually train on these math datasets, you see you do get better in general. But if you train on DeepSeekMath corpus, you get a lot better, as you can see right here. So two notable things. One notable thing is that there's a clear trend as your training datasets get bigger, the performance increases, meaning that even in this sort of targeted data scenario, having more data is important. Now, the base model will have had already a lot of training data. So it's not just more data of any kind, but more relevant data. And that's why it is important that this paper develops a method to find relevant and, let's say, high quality, but I guess mostly relevant in the way they classify it, relevant data at scale. So more data is still better, but it needs to be in the domain that you use it for. Otherwise, it doesn't do you much good. So more data is better in this sense, but also what you can see is that because this is not a constructed data set, it's like a scraped, collected, classified data set from the general internet, it does also perform well on what they call later Chinese benchmarks. So it's also more multilingual than the other data sets, and that makes it benefit also on multilingual data sets. So the gain is larger in the Chinese benchmarks than in the English benchmarks because the reference data set, they are more monolingual in the way they're constructed. All right. Yeah, they point out here, okay, our data is high quality because our model is good. The high quality is, we talked about this in the paper discussion. It's, what does high quality data mean? Nobody really knows. I would say it's relevant data, like not high quality means relevant. I would classify this corpus in particular more as like the feature is more that it's relevant rather than high quality, which is a very vague term in a sense. In any way, they say, okay, we're better, which could also be due to the fact that they just have more relevant data. It doesn't need to be higher quality necessarily. It's multilingual and it's large scale, several times larger than existing mathematical corpora. All right, so now they have a good data set. Now they are actually going to build their real model, if you will. They built this DeepSeekMath base 7B model, a 7 billion parameter model that is initialized with DeepSeek Coder base 1.57B. So they make a deliberate choice to start out with a model that's pre-trained on code. And they have some justifications further down where they evaluate different pre-training modalities, and they do find that code pre-training is very relevant for these kinds of math problems. Interestingly, they also find that pre-training on archive is not so important, at least in isolation. So if you just train on archive, the benefit for the downstream performance of these kinds of math benchmarks seems to be very, very little or very minimal. I would guess that you can explain that by the fact that archive papers are mostly about communicating math and not necessarily about kind of deriving solutions in math. Someone in the paper discussion also pointed out, which is correct, that you don't really put the derivations if you actually solve something, let's say, you just kind of pose the starting point like, okay, we assume these things, and then you pose the end and say, this can be reformulated into this right here. And very, very often there's no explicit derivation or goal direction or something like this. So if pre-training on archive seems to teach the model maybe more about LaTeX and math notation rather than actually solving mathematical problems. Two different things. Okay, so they take their data set and they mix it with a bunch of other data set. 56% is their data set, then some algebra stack. They do include archive here. They do include GitHub, and they do include some natural language data from Common Crawl in both English and Chinese, and they train for 500 billion tokens. So their own data set has 120 billion tokens, and they add some other data on top. So since this is 56%, we can guess that gets them to about 200 and some billion tokens. So they go through the data set twice, if you will, during their training. You can see here what this does. This specifically, there are two tables right here. The top one measures simply chain of thought prompting on these math puzzles, and the bottom one measures tool use. So if the model is allowed to use some external Python environment to do computations, or a proof environment, I think. I guess most people are, well, I guess both are interesting. As you could have imagined, as you could have guessed, since it's their paper, they do outperform everything else by quite a significant margin, including models that are specifically trained to do this kind of thing, like theirs is, including models that are several orders of magnitude larger than they are, like this 540 billion parameter model right here, which is impressive. The same goes for tool use. So if you consider problem solving with tools, and also a related category, informal to formal proving, where they have to prove some statement in a formal fashion or formalize some proof, the model also performs quite well. I'll let you dig into these benchmarks by yourself, but just note that the differences are significant. It's not just like, oh, we got 0.1% better on some benchmark. The benefits here are consistent and significant. Now, this is not where it stops. So they now have a model that's been pre-trained on code, and further kind of language model trained on their collected math corpus. Now they go further and they say, can we also do some instruction fine-tuning? So they take a data set. They say we annotate GSM-8K and math problems with tool integrated solutions and adopt a subset of math instruct along with training set of Lila OOD, where problems are solved with chain of thought or program of thought. These are prompting techniques. So they construct a fine-tuning data set where models are, where they're specifically shown how to solve problems using chain of thought, because it's one thing to do chain of thought prompting with a regularly trained language model, but it's another thing to explicitly teach the model with training data how to do chain of thought. I think they construct this data set, or data sets in English and Chinese, and they train on for about 500 steps with a batch size of 256. So as you can see right here, this is what, 2 to the 8, this is 2 to the 9, so that's like 2 to the 17. This is not super many data points, right? So it's just, we know this, if you want an instruction tune, you don't actually need that much data. Like 2 to the 17 is what? I don't know, but not much. 2 to the 10, yeah, it's like 100,000 or something. Cool. Results are down here. As you can see, the best models still in this kind of benchmarks are, closed sourced models like GPT-4, Gemini-Ultra. they do reach quite some performance, although not so good in Chinese. However, as you can see here, this instruction tuning already gets these models beyond most open source models and very close to these closed source models, actually beating a lot of the closed source models as well. And if we go further and do RL on top, so reinforcement learning on top, you can see that they surpass all open source models, even open source models that are 10 times larger than they themselves are, even open source models that are 10 times larger and trained on math. So that is quite impressive. They also achieve a good performance, like same qualities on Chinese. And again, they get really, really close to these many times larger closed source models. So what is this final RL, this final reinforcement learning step? So on top of the supervised fine-tuning, the instruction tuning, they now go and they do this reinforcement learning using group relative policy optimization. So GRPO, in short, is a variant of proximal policy optimization. Now, in reinforcement learning, you typically, right, the setup is you have some actor and you have some environment. And what you do is from the environment gives you what's called an observation. In this particular case, the environment gives you a question or a math problem. That's the question that the environment gives you. And then what you do is you give an action. And the action in this case, we call O, the output of your model. So you get a math question and you're supposed to deliver an output, which is, whatever your language model outputs. Maybe it has some chain of thought prompting in it and blah, blah, blah. But at the end, there should be the solution. Notably, the environment then responds with a reward. And the reward in this case is either you did it or you didn't do it. So the environment will look at your solution, see at the end, did you get the correct solution, and give you a reward or give you no reward. And the process of reinforcement learning is this actor here internally will have some sort of neural network, and we usually call this the policy. So the policy, pi, usually denoted, it will take an observation and it will output an action. This is our LLM. So our LLM is the policy, if you will. Usually you denote pi theta to denote that the policy is parameterized. So this is the same as essentially writing that the output is what you get when you stick your question into the LLM together with your LLM parameters. I mean, you can write this here or you can write it here, just showing that your LLM is parameterized. And the task of reinforcement learning is, can you train your LLM? Can you fine-tune your LLM to make the reward go up? The problem is, usually you have a loss function. Usually you're going to have your O, you're going to stick it into a loss function of O and O. I don't know how to denote this. O, not hat. Hat is the approximate one. So let's say this is your output. I'm gonna check O check mark. Okay. So we have the correct answer right here, and we have your answer right here, and we're gonna stick it into a loss function, usually something like cross entropy, and then we can take the gradient with respect to the parameters of that loss function, and that is perfect. We can do back propagation, we can train. In reinforcement learning, that's not possible because you have no clue how this reward is being done. Maybe it's a human looking at it and saying, good job. Maybe it's an LLM as a judge. Maybe it's a regex or something like this. But for sure, it's not differentiable. So that's the challenge of reinforcement learning, and many, many techniques have been evolved, notably one that's called TRPO. TRPO, Trust Region Policy Optimization, is itself a mixture between trust region optimization and, applied to policy learning. And then this has been approximated in an algorithm called PPO, Proximal Policy Optimization. And the group policy optimization is another derivation. Group relative policy optimization is another derivation from PPO. So very briefly, if you already know a lot about reinforcement learning, these next 2 minutes might bore you, but very briefly, when we do policy, like when we tackle this problem right here, there are a couple of different variants of reinforcement learning, but we're mostly concerned with a thing that's called policy learning, which is exactly our case here, where our policy is directly parameterized with parameters. So we have a function that takes in the observation and spits out the action, right? And that function itself has parameters that can be learned, which is different to, for example, Q learning, is where you learn the Q function and then the action is simply derived as a, you look at which action makes the Q function go up. But in this case, the policy is directly parameterized and we want to learn the policy. So ultimately, we are after a d theta, like a what or a delta theta. Like how should we update our parameters? Usually that is the gradient of the loss function with respect to theta. Okay, that's our usual step, maybe with some step size, and then we do gradient descent. We cannot do this here. What we can do is something called the method is called reinforce. Which is the following. It's easier to think of not like language model learning. It's easier to think of Pac-Man. Okay, so here is Pac-Man. Boop, boop, boop. And you have, at any point, you have 4 actions. Go right, go up, go left, or go down. Okay. Those are your 4 actions that you have available, and you need to choose one. Each frame, you need to choose an action. Okay. And then boop, 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 boop. And depending, the observation is the whole board. Now, what you do, again, you stick your observation into your policy, and out comes some action. The action then goes into your environment, and that gives you your reward. The problem is you don't have a loss function, so you don't know whether your action was correct or not. In a usual classification problem, you would know whether your action is correct or not, and you would have a cross entropy loss. So what you do here is you simply assume, you just assume that what you did, the action you took, is the correct action. And bear with me for all the people protesting now. What that, if you have that your cross entropy loss actually just reduces. So your loss actually just reduces to be the log policy of your observation. Okay, so if you assume that the action you did is the correct action, then it's just this, because you'll have output some kind of distribution. Okay, you do this action that's the highest here, and you compare that, you do the cross entropy loss with a distribution that's 0, 0, 1, 0. Right? That's ultimately what you do in a cross entropy distribution. You do a one-hot encoding of the correct label, and then you compare. Okay, and now you multiply that with your reward. Okay, what does this do? Actually, negative maybe. So maybe that's the loss or the objective function. Not really sure whether negative or positive, but the sense here is if your reward is high, then you are in fact correct in assuming that what you did is the correct thing, and therefore this will be very valid, right? However, if your reward is low, then you are incorrect in assuming that what you did is the correct thing. But since you multiply by a number that's low, it will, not be as impactful. So specifically, if we now talk about taking the gradient of this function, this is no longer the loss here, but specifically if we're talking about taking the gradient of this function and then using this as our delta, it means the direction we move into will be, let's say your reward is high, then it is this direction, which assumes that our label was the correct one, which means that in the future, given the same observation, we're going to repeat that action. Right? That's what it means if we do gradient descent on with that action being the correct label. So in the future, you'll do more of that, and you multiply that by a big number, so good. If your reward is low, then you will do less more of that in the future. Okay, so that's the trick. Multiplying it by the reward kind of modulates how that assumption is taken into account. Now, usually you actually don't multiply by the reward, but you multiply what's called the advantage A. The advantage A is a normalized version of the reward, and the advantage is usually just your reward minus some baseline. And the baseline, we're going to get into that. So theoretically, the baseline just has to be any function of the current observation as long as it doesn't depend on the action that's being done. So the reward depends on the observation and the action, obviously. So you get an observation, you act, and then you get a reward. As long as the baseline only depends on the observation, then you can actually use any baseline function that you want to subtract here. But what people usually do is they subtract what's called the value function. So the value function is another function that you train on your trajectories that tries to estimate what's the average reward I'm going to get in this particular situation. Like what's the, on average, performing kind of the actions in the way that I perform them or performed them in the past. What is it? And what you can see right here is if you actually manage to do that, then the advantage will be greater than 0 if your reward was higher than average, so more than you expected, and the advantage will be less than 0 if your reward was lower than average. So if you did a thing and actually it goes well, it goes better than average, then A will be a positive number, so you'll do more of that action in the future. And if you do a thing, given the observation, that leads to a reward that's less than expected, the advantage will actually be less than 0. And you'll train not just to do less of the, you'll actually actively try to avoid that in the future, right? So you'll go into the opposite direction of this, which assumes that you did the correct thing. So you'll go in the opposite direction. Notice that this is still different from having a label, right? The difference is, so in the situation where you did the right thing, there's no difference, right? You assume it's the correct label. It is actually the correct label. Good, that's the same as a classification task. But in the situation where you're incorrect, in this reinforcement learning setting, all you can do is avoid doing that action in the future, right? So Pac-Man, you went right, you got eaten, don't do that anymore. Whereas in a classification task, if you have a label and you went right, your loss could tell you, no, you should have gone up, right? That's the difference. So either just avoiding this versus actually knowing what the correct thing is. As you can see, if your action space becomes complex, those two things are quite a difference. But obviously, once we get into the realm where we just don't have label training data anymore, we have no choice but to do this. Okay, all of this being said, that usually we have some sort of our policy times our advantage. Now, what does TRPO, PPO, GRPO, what do they do? TRPO comes from a trust region approach. So a trust region approach is, I am here, my gradient tells me to go there, but I don't trust my gradient too much. It's dangerous to trust noisy stochastic gradient. Like you just have one mini batch of samples and you just evaluate it, and the gradient is just a linear approximation. So should I really go very, very far into that direction? I don't think so. So why don't I make what's called a trust region approach? Now you can do hard trust region where it's just like you can go this far but no further. But what's usually done is you usually say, okay, let's go. Your loss function is actually a function of your actual loss, like be that classification or reward, like the thing that we have down here or something like this, plus some KL divergence between where you want to go, right? This here is pi hat, that's like where you would like to go, and this is pi, where you are currently. So between these two, a KL divergence, it's a measure of, be careful that I don't upset the mathematicians. It's a distance. It's a pure valid distance function between this. It's a thing, and if these two distributions are more different, the number grows. Let's just say it like that. So you can see that there is a kind of a tug of war at play. So the gradient descent wants very often the policy to move quite far in a particular step, versus this KL divergence penalty forces it to stay close to whatever reference policy you have. TRPO does this with by computing the natural gradient descent, like doing a second order approximation, adjusting to the curvature of the landscape, and then doing a line search. So you need to compute the Hessian, you need to do line searches and so on. This is all very, very cumbersome, uses second derivatives, very, very bad if you're dealing with large models, and therefore PPO was developed. PPO is an approximation to that, and that's the first formula that we actually encounter here. Encounter here. Okay, so PPO is, and you can see the formula is quite a beast, but we'll go through it. In a sense, you can see that the objective function has at its core again, it has at its core again the policy times the advantage. Hope you can see that. So at its core, it's the same thing as reinforce. However, it modulates that a bit. It essentially says that what we care about is the likelihood ratio between pi and here pi old. Now there's a bit of confusion sometimes with this kind of notation, like what is pi old? What kind of old thing? Are you maintaining two different policies? Is there like an old model and a new model or something like this? And that's not the case. So this top thing, that's the thing we're currently optimizing. And this thing here is the thing that created the current action and observation. So only the bottom one is actually a real model that you have instantiated and that generated the data, right? That got this question and that produced these outputs. And the top thing is the thing you're currently maximizing. So you were here and that's what you generated your data. And now you're kind of considering the whole space here of, where should I go? And wherever you consider, that's the new thing, right? That's the thing that you're actively maximizing currently. So you can also write this as pi theta times a divided by pi theta old, right? This is the model you're optimizing, and this is just a number. Right? This is just a number that says how well did you do currently, and how likely is the thing you did under the old policy, under the policy that created it. So the idea being that you want to find something that did well, right? That gets a high reward, but also something that's quite likely from the place, you know, where you currently are. What you don't want is you don't want to find some kind of exploit in the environment, some kind of niche, some kind of adversarial example almost. You don't want to find that just shoots up your reward. Like, let's say you did something. You sampled from your policy and you did something and it turned out well, right? And now if you didn't have this down here, now if you were to just maximize this policy with respect to theta, you would essentially look for the parameters you essentially ask yourself, what did I do to cause this good thing? And let's do a lot more of that, which sometimes is good, but if you have a long action sequence, you've probably, let's say you're a language model and you output a chain of mathematical thought, and somewhere in between you use the word banana just by happenstance, and you're like, I use the word banana. That like, let's do that a lot more, even though that might not be responsible for this. So conservatism is built into this algorithm, right? Like in the trust region sense, we are saying, yes, if something good happens, please go into that, do more of whatever you did. But whatever you end up doing must still be kind of likely under the policy that, generated the data. So I hope that's kind of, if you don't have that, then it gets very unstable. And then you start, your training procedure essentially starts just going after these kind of exploits that just by happenstance correlated for a little bit with high reward or low reward. On the other hand, so this is one conservatism, is this ratio. The second conservatism is you're actually taking a minimum of this quantity and this clip quantity right here, which means that even this ratio you actually constrain to be in a region of 1 minus epsilon to 1 plus epsilon. So this ratio you're not going to let go out of whack very high. So you constrain it as well. And then you take the minimum of the two. So there are several layers of conservatism built directly into this objective function of PPO. And that conservatism combined with the fact that in their reward model that they use, so their reward is actually modified. They subtract this right here, which is, and this might be familiar to you, this here is a KL penalty from a reference model. Now, sorry if this is confusing, but there's another model coming. So this model here, what we call the reference model, that's the model you started with. So this reference model here would be the model from SFT fine-tuning. So you're pre-training with code. That will, here's your initialization, you're pre-training with code, that will land you here in the weight space, and then, or in the policy space. And then you're pre-training further with this math corpus, that will land you here. And then you do SFT, supervised fine-tuning, that will land you here. And here you're doing RL. But you are, by adding this right here, you are actively pushing back towards that initial state. You're assuming, okay, the thing I started with isn't actually so bad, it's kind of reasonable, please don't move away from that. Now, you've already seen this in GRPO. The difference is here we're simply adding that penalty to the reward function. We're not going to compute any second derivatives or something like this. We're essentially simply saying, yeah, even if your reward is good, if it requires you to go away very far from where we started training, it's actually you pay a penalty. You don't get as much reward. So that means the further away you go, even if you collect super high reward from the environment, it's just subtracted. You just pay a tax essentially from going away. So that's where they implement the KL penalty rather in the overall objective. So in overview, PPO looks like the thing on top right here schematically. You have a question, your policy model, like your LLM, produces an answer that goes through. So your reward isn't directly used. Your reward actually goes through a reward model. The reward model is simply a substitute for the environment that's trained on the environment. Has some advantages to have a reward model. But essentially, you can just think of that as the reward. As said, there is a reference model that estimates the likelihood of what you did and gives you a KL penalty if what you did isn't so likely under the model you started training with. That will give you your reward. Then there is a value model that also takes the observation and, the value model, I'm not sure if it actually takes O or if it takes Q. Could just take Q maybe. Well, in any case, the value model gives you the value of the current situation, which then allows you to compute the advantage. And the advantage is what you use to train the policy model, given this loss function we saw before. So you can see this includes training this value model right here to do this advantage estimation, to variance reduce the reward for reinforce, to then do the gradient descent here. So you need the advantage. Now, the bad thing is you need a value model, and the value model is also some big language model that doesn't output text, but outputs a number. But still, it needs to be a performant model that is able to ingest, text from, look at the environment, look at the things, and then be powerful enough to predict the average reward that you're going to get in a certain situation. And that's not very good if you're dealing with LLMs, because there are already billions of parameters, and therefore it's not so fun to maintain two of them at the same time. So group reference policy optimization says, well, we can just leave it away, we don't need it. And then someone will say, okay, how then do you compute the advantage, right? What do you do instead of the value model? And that's where GRPO simply says, well, look, we can use any baseline we want. So how about we do this? Instead of just getting one, so for Q, instead of just getting one observation, actually we get a ton of observations. So O1, O2, O3, O4. Like we just kind of spray sample. And then we use the reward model to estimate the reward for each of them. Reward 3, reward 4. And then, as our baseline, we can actually use the mean of all of these rewards divided by the standard deviation of all of these rewards. So in essence, we're just doing a z-score normalization across that. We're using the statistics of various outputs as a baseline. Essentially, it makes sense, right? It's okay. What does the value model do? The value model estimates what's kind of the average reward you're going to get in this situation. Well, I have a language model, so I can just sample a whole bunch of times according to the language model, like according to my policy, right? Sample a whole bunch of times and just look at what kind of rewards would I get by sampling a whole bunch of times, and then use that as my baseline, saying, well, clearly that thing is my average reward. So it's not exactly the baseline like what we end up doing, and you can see that here. We end up actually doing, yeah, so you can see it's a bit different. It's not minus the baseline. We end up doing the reward minus the mean divided by the standard deviation. So we're z-score normalizing the reward, and that is our advantage. We can do that because we have a reward model, so we don't always have to submit to the environment. And we can do that because we have language models, which we can just roll out given a certain prompt. We can just roll out at a certain temperature a number of times and therefore get that distribution. And that means we don't need to have a value model. So other than that, pretty similar. They do one other difference is that they return to adding the KL penalty directly to the objective function rather than penalizing the reward. Yeah, it's a choice. And oh, sorry, yeah, they approximate it using this formula right here, since don't want to compute the Hessian and whatnot. They do an approximation like this. So this is instead of adding it to the reward like PPO does. So that's a second slight difference other than just leaving away the value model. Cool, that's it. That's what they do. That's how they get rid of the value model, and by using the LLM. So in practice, they're going to have not just one question, but they're going to have question 1, question 2, question 3, question 4, and so on. To each of them, they are computing a whole bunch of outputs like 011, 012, 013, and so on. So, and then they normalize within those groups, right? And that's why it's called group relative policy optimization, because this is a group, and this is a group, and this is a group, and this is a group. So each question you roll out individually a bunch of times given the same starting point, and that's what gives you your ultimate value or your ultimate advantage for that particular group and advantage for that particular group, and so on. So you just stratify, in a sense, by sample. Yeah, that's it. They go into how they also do process supervision, which you can do when you have this kind of chain of thought things, which is if you somehow manage to have a reward model that can give you even reward for intermediate results, like you do chain of thought prompting. So in math, you have derivation steps. If you can somehow train a reward model that can recognize, oh yeah, that's a correct derivation step, you're on the correct path, and can already give you a reward, right? That also pairs quite well with the GRPO. It probably pair quite well with any RL algorithm. But you can just do this thing by this intermediate reasoning steps. And yeah, that's it. So yeah, don't want to go into the super duper details other than that, but I do think it's an interesting paper. One thing that I do want to and yeah, you see like above, they using this GRPO, they then push their performance even further, right? And that's how they get beyond all open source models and close to the commercial models. Now, this is the last thing I want to highlight, this section on why RL works. So here they evaluate different things. They evaluate specifically pass at K and Maj at K. Maj at K is like majority voting. So what you do is you have a model, you have a question, and you output not just one output, but you output like an ordered set. Okay, so you like give me your top 20 answers, right? So you get 01, that's your best, the answer that the model wants to give most, and then you give the second most answer and the third most answer and so on. And they could all be correct, right? Just different reformulations, let's say, of the same answer, different or different derivations or same derivations stated in different ways or something like this. But essentially what you're interested in is how many of the top k results are correct in itself. That's the pass at k. And if you had to, vote, if majority voting on the top k, how often would you be correct then? There's a slight difference, right? And that slight difference is actually made more drastic by reinforcement learning. So they say here, as shown in figure 7, reinforcement learning enhances majority at k's performance, but not pass at k. These findings indicate that reinforcement learning enhances the model's overall performance by rendering the output distribution more robust. In other words, it seems that the improvement is attributed to boosting the correct response from top k rather than the enhancement of fundamental capabilities. This is something that we've come to learn in a lot of different ways from like reinforcement learning on language models or even supervised fine-tuning, is that what's happening most likely is more that the capabilities of doing all of these things are already present in the underlying pre-trained language model. And what these fine-tuning things do is just they kind of shape that output distribution. So maybe the model has all kinds of ideas of what to say, but you kind of suppress the paths that you don't like, that are not according to your objective, according to your SFT distribution, right? If your SFT distribution is this chain of thought stuff, then you just kind of suppress all the output distribution that doesn't do that, and you push the output distribution that does. But notably, that distribution is already there. All that's needed is to kind of bring it up from the capabilities that the model already has. And that, in a sense, is good and bad news. The good news is that, yeah, it probably doesn't require that much data, that much effort, or that much compute to do these kind of things, because all that's needed is sort of shaping a thing that's already there. The bad thing is that given underlying models, there seems to be, the natural ceiling of how far we can push these models using reinforcement learning and self-tuning and so on is probably lower than many people expect, right? Because what we're ultimately doing with RL and test time compute investments and whatnot is just kind of bringing up what's already there in these models. And yeah, that will quickly reach its limit. Obviously, reinforcement learning, given enough time, can solve any problem in the theoretical limit, but that's not the real world. And yeah, I think works like this show clearly that if we want AGI, we might not get it with staying at the current pre-trained models and just trying to tickle them in particular ways and sample them in particular ways, unless you think that some like AGI is already hidden inside of these models and we just have to bring it out. That's of course possible, but I personally believe that that's not the case, and we are still going to need to iterate on actually the base models to become a lot better, rather than just doing a lot of test time compute, which is very popular right now, or fine-tuning or RL or something like this. All right, this video is already too long. I thank you very much for listening, and yeah, join us on Saturdays. It's always fun. See you around. Bye bye.